Hello again, statistics buffs. I know that many of you have pets, although you're not supposed to have them in dorms. A lot of you keep little marine arthropods. They're just so cute. Here's a picture of one of them I took over in the dorm the other day. There's a cute little marine arthropod. They are so cute, I decided that as a graduate student in marine biology, I will feature them in my doctoral dissertation. So, by the way, I'm making up this narrative. It's actually a problem coming from a book called Biostatistical Analysis, 5th edition, by Jerrold Zar. At any rate, I'll continue pretending that I'm a marine biology graduate student, and I go to the local pond where I find these little marine creatures, and I sample 13 of them, and I measure in them, I measure the calcium concentration in millimoles per kilogram in their coelomic fluids, assuming these are little coelomates. So when I do that, 13 of them I pull out, and I get way over here, I get the calcium concentration in millimoles per kilogram. And in the water, the concentration is 32 millimoles per kilogram. Well, the general opinion of people has been up to now, without anybody really studying it, is that the mean value of the population of these little critters is equal to that of the calcium concentration in the water. That is, somehow they exchange calcium in such a way that the two always equilibrate. Well, I don't think I believe that. I'm going to write my dissertation, and I'm going to make a claim for my dissertation, and my claim is that the population mean is less than the concentration of calcium in the water. That is to say, I'm going to make a claim, C-L-A-I-M, that the calcium concentration in the coelomates is less than the calcium concentration in the water. The counterclaim, the generally held view, is that the calcium concentration in the coelomate itself is equal to or greater than the calcium concentration in the coelomic fluid, in the water, I should say. So this is the coelomic fluid. I'll use the subscript CF to keep those two straight. Okay. So now I'm going to frame these claims in terms of a hypothesis test. The null hypothesis is a hypothesis or the claim which contains the equal sign, which in this case is a counterclaim. So the counterclaim is the null hypothesis is this. My research claim, my alternative claim, hypothesis, is that the concentration of calcium in the coelomic fluid is less than the calcium concentration in the water in which they are found. And I want to test that. I'm going to test H1 against H0 at a level of significance of 0.050. Well, how do I do that? I need to do two things. I need to find a critical value of t. This is a small sample, fewer than 30. So I'm looking for t, and in our notation I'm looking for t, which corresponds to an alpha. This is of 0.05. This is a one-tailed test. Happens to be on the left. And the other value here, this is going to be one-tailed test, so I'll put a little parenthesis 1 indicating that. A little addition to our previous notation. And degrees of freedom are 1 less than the sample size. The sample size was 13. 1 less than 13 is 12. So this is my critical value. So I have to look it up. I'll look it up in a table. I will look under an alpha equals 0.05 for a one-tailed test down to the 12 degree of freedom row. If I do that, I find that that is approximately equal to 1.782. So on the left side, so I will put in a minus sign, pointing to the left, so this will be a minus sign. The next thing I need to do is calculate a test statistic, which in this case is just t, which is my sample mean minus the population mean of the null hypothesis, which is 32 millimoles per kilogram. I divide this by the standard deviation of the sampling distribution of sample means, which of course I don't know, but I can approximate it this way. It is equal to the standard deviation of the sample divided by the square root of the sample size. So all I have to do is calculate that and compare it to minus 1.782. So to do that, I need some data. So I'll go back to the data, and I will find here, if I go to the Data tab, Data Analysis, I want to do something we did years ago, descriptive statistics. That will tell me the mean and the standard error, which is what my denominator there is called. So I will choose, I've already chosen, but I will choose again the input range. It's column A, rows 3 through 15, and I'm going to choose those, and I'm also going to choose as an output range. I'll put them right here. I will report the summary statistics, so I'll put a check mark there. And it looks like I'm ready to go. I'm not going to put in any confidence limits for the mean or such at this stage. So I have an input range, this column, column A, rows 3 through 15, and I'm going to put the descriptive statistics with the left-hand upper corner right there. So I'm going to then click OK, and there we are. There are my statistics. I'll replace this column 1 business by CA, not VA, CA in square brackets, which to biologists and chemists means calcium concentration. Millimoles per kilogram. And we'll see what we get. We see that we have a value for the mean of 29.7692, something or other. So I'll put that in here. I'll change color here, try a indicate the typing. Change colors. Okay. This is equal to x bar, which is 29. I've already forgotten the remaining digits. 769. Hypothesized null hypothesis mean value was 32. And I'll divide that by the standard error, which is what this quantity is. That's the standard error, abbreviated SE. It's calculated for me over here, 4955. 0.4955. I just have to do the arithmetic now, which I will do on my computer's calculator. Put in a 29.769 minus 32 equals minus 2.231, and I will then divide that by the standard error, which was 0.4955, and I'll get minus 5025. This is 0. So there's my test statistic. I need to compare that to my hypothesis here. You'll notice that my test statistic is more extreme. That is to the left of the critical value. Therefore, I must reject the null hypothesis at this 0.05 level of significance. In other words, my thesis is supported.